My dear students, welcome back to our channel. In this video, I will be explaining the MCA second semester subject Operations Research as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 2 first important short question is: define transportation problem. Transportation problem. A transportation problem is a special type of linear programming problem, LPP, that deals with transporting goods from sources, like factories or warehouse, to destinations, like markets or shops, in such a way that the total transportation cost is minimum or profit is maximum while satisfying supply and demand conditions. Key points. Each source has a limited supply of goods. Each destination has a specific demand. The objective is to find the best allocation of goods from sources to destinations. Example. Suppose a factory in Hyderabad can supply 40 units and another in Vijayawada can supply 60 units. Two markets in Chennai and Bangalore demand 50 units each. The cost of transporting from each factory to each market is different. The transportation problem helps decide how many units to send from each factory to each market so that total cost is minimum while meeting all demands. Easy to remember, think of it as a goods delivery optimization problem. Next important short question is: 2. What is a balanced and unbalanced transportation problem? Balanced and unbalanced transportation problem. A transportation problem is said to be balanced when the total supply is equal to total demand. In this case, all the available goods can be transported, and all the demand can be satisfied without shortage or surplus. Example, if 3 factories supply 30, 40, and 50 units, total 120, and 3 markets demand 20, 60, and 40 units, total 120, the problem is balanced. An unbalanced transportation problem occurs when the total supply is not equal to total demand. If supply-demand, we add a dummy destination to absorb the extra supply. If demand-supply, we add a dummy source to meet the extra demand. This makes the problem balanced so that it can be solved using regular methods. Example, if supply is equal to 100 units but demand is equal to 120 units, we add a dummy supply of 20 units. Easy trick to remember. Equal is equal to balanced. Not equal is equal to unbalanced, make it balanced with dummy. Next important short question is: 3. What is the difference between feasible and optimal solution in transportation problems? Feasible versus optimal solution in transportation problems. In a transportation problem, we deal with sending goods from sources to destinations at minimum cost. While solving, we first find a feasible solution and then improve it to get an optimal solution. A feasible solution is any solution that satisfies all supply and demand conditions without breaking any rules. It may not give the minimum cost. Example, if supply is 100 units and demand is 100 units, and we allocate goods in such a way that all requirements are met, that's a feasible solution. An optimal solution is the best possible solution that not only satisfies supply and demand but also gives the minimum transportation cost or maximum profit. Example, from all feasible ways of transporting goods, the one with the lowest total cost is the optimal solution. Easy way to remember. Feasible is equal to possible, valid but not best. Optimal is equal to best, valid plus minimum cost. Next important short question is: 4. Define transshipment problem. Transshipment problem. A transshipment problem is an extension of the transportation problem where goods are not sent directly from sources to destinations, but may pass through intermediate points like warehouse, depots, or distribution centers before reaching the final destination. This situation happens in real life when direct transport is costly or not available. Transshipment allows goods to be shipped, stored, and then forwarded in the cheapest way. Example: a factory in Hyderabad produces 100 units. Demand exists in Chennai and Bangalore. Instead of sending goods directly, which is costly, the company first sends goods to a warehouse in Vijayawada and then distributes them to Chennai and Bangalore. Here, Vijayawada acts as a transshipment point. The goal is still the same: minimize total cost while meeting demand. Easy way to remember. Transportation is equal to direct. Transshipment is equal to with stopovers via intermediate points. Next important short question is: 5. Distinguish between degenerate and non-degenerate transportation problem. Degenerate versus non-degenerate transportation problem. In a transportation problem, while solving, the number of allocations, occupied cells, in the initial or intermediate solution is very important. A non-degenerate transportation problem occurs when the number of allocations in the solution is exactly m plus n1, where m is equal to number of rows, sources, n is equal to number of columns, destinations. This is the normal case, and the solution can be easily tested for optimality. Example: if there are 3 sources and 4 destinations, the required allocations is equal to 3 plus 4, 1 is equal to 6. If exactly 6 cells are filled, it is non-degenerate. A degenerate transportation problem occurs when the number of allocations is less than m plus n1. This creates difficulty in testing for optimality and requires adding a very small value, epsilon, in an empty cell to remove degeneracy. Example: if only 5 cells are filled instead of 6, the solution is degenerate. Easy trick. Exact allocations is equal to non-degenerate. Less allocations is equal to degenerate, needs epsilon. Next unit 2, transportation problem. Top 5 long questions. First important long question is: explain the steps to formulate a mathematical model for a transportation problem with example. Steps to formulate a mathematical model for a transportation problem. A transportation problem, TP, is about sending goods from sources, factories, warehouse, to destinations, markets, shops, at minimum cost while satisfying supply and demand. To solve it, we first formulate a mathematical model. Steps of formulation. 1. Identify sources and destinations. Suppose there are m sources, factories, and n destinations, markets. Let the supply at source I be A and demand at destination J be B. 2. Define decision variables. Let x is equal to number of units transported from source I to destination J. 3. Objective function. Each unit transported from source I to destination J has a cost C. Total transportation cost is equal to Z is equal to sigma Cx, where I is equal to 1 m, J is equal to 1 n. The goal is to minimize Z. 4. Constraints. Supply constraints. From each source, total supply cannot exceed available units. Sigma x is equal to A for each I. Demand constraints. Each destination must receive its demand. Sigma x is equal to B for each J. Non-negativity, x greater than or equal to 0. Example: a company has 2 factories, F1, F2, and 2 markets, M1, M2. F1 can supply 20 units, F2 can supply 30 units. M1 needs 25 units, M2 needs 25 units. Costs per unit in are M1 M2 supply F1 4620, F2 5330. Demand 2525. Formulation. Decision variables x, 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 x. Objective, minimize z is equal to 4x plus 6x plus 5x plus 3x. Constraints. X plus x is equal to 20, supply F1. X plus x is equal to 30, supply F2. X plus x is equal to 25, demand M1. X plus x is equal to 25, demand M2. X greater than or equal to 0. Easy way to remember decision variables objective constraints. Next important long question is: to solve a transportation problem using northwest corner rule, NWCR. Solving a transportation problem using northwest corner rule, NWCR. The northwest corner rule, NWCR, is a simple method to find an initial basic feasible solution, IBFS, for a transportation problem. It is called so because we start allocations from the top left, northwest, corner of the cost table and proceed step by step. Steps of NWCR. 1. Start with the northwest corner cell of the transportation table. 2. Allocate the minimum of supply or demand to that cell. 3. Adjust the supply and demand by subtracting the allocated value. 4. If supply is exhausted, move down to the next row. If demand is exhausted, move right to the next column. 5. Repeat until all supply and demand are satisfied. Example. A company has 2 factories, F1 F2, and 2 markets, M1 M2. M1 M2 supply F1 4620, F2 5330. Demand 2525. Step 1. Start at F1 M1. Supply is equal to 20, demand is equal to 25, allocate 20. Now F1 supply is equal to 0, M1 demand left is equal to 5. Step 2. Move down to F2 M1. Supply is equal to 30, demand is equal to 5, allocate 5. Now F2 supply is equal to 25, M1 demand is equal to 0. Step 3. Move right to F2 M2. Supply is equal to 25, demand is equal to 25, allocate 25. Now all supply and demand are satisfied. Final allocations. X is equal to 20, X is equal to 5, X is equal to 25. Total cost is equal to 20 times 4 plus 5 times 5 plus 25 times 3 is equal to 80 plus 25 plus 75 is equal to 180 rupees. Easy way to remember. Start from top left. Allocate min, supply, demand. Move down or right until finished. NWCR is quick, though it may not give the optimal solution directly. Next important long question is: 3. Describe the least cost method and solve a problem using it. Least cost method, LCM. The least cost method finds an initial basic feasible solution, IBFS, for a transportation problem by always allocating to the cell with the smallest transportation cost first. This usually gives a better starting solution, lower cost, than NWCR. Steps. 1. Look at all cells and find the least cost cell. 2. Allocate as much as possible to that cell, min, supply, demand. 3. Reduce the corresponding row supply and column demand by the allocated amount. 4. Cross out any row or column that becomes 0, exhausted. 5. From the remaining cells, pick the new least cost cell and repeat until all supplies and demands are met. 6. If there is a tie in costs, break tie by choosing the cell with larger supply or demand or any consistent rule. Example. Same data as before. M1 M2 supply. F1 4 6 20. F2 5 3 30. Demand 25 25. Step 1. Smallest cost is 3 at F2 M2. Allocate min 30 25 is equal to 25x is equal to 25. Now F2 supply is equal to 5, M2 demand is equal to 0. Cross out column M2. Step 2. Remaining cells costs F1, M1 is equal to 4, F1, M2 crossed F2, M1 is equal to 5. Least is 4 at F1, M1. Allocate min 20, 25 is equal to 20x is equal to 20. Now F1 supply is equal to 0, M1 demand is equal to 5. Cross out row F1. Step 3. Only cell left is F2 M1. Allocate remaining 5x is equal to 5. All supply demand satisfied. Final allocations. X is equal to 20, X is equal to 5, X is equal to 25. Total cost is equal to 20 times 4 plus 5 times 5 plus 25 times 3 is equal to 80 plus 25 plus 75 is equal to 180 rupees. Remember, LCM is equal to always pick the cheapest cell and fill it. It gives a better IBFS than NWCR most times, but still may not be optimal. Use Modi or stepping stone method next to test improve. Would you like the same example shown as a filled table image for quick revision? Next important long question is 4. Explain the Vogel's approximation method, VAM, with an example. Vogel's approximation method, VAM. The Vogel's approximation method, VAM, is another technique to find an initial basic feasible solution, IBFS, for a transportation problem. It usually gives a much better starting solution, closer to optimal, than the northwest corner rule, NWCR, or least cost method, LCM. Steps of VAM. 1. For each row and column, find the penalty is equal to difference between the two smallest costs. 2. Identify the row or column with the highest penalty. This shows where a wrong choice costs the most. 3. In that row column, select the cell with the least cost and allocate as much as possible min of supply, demand. 4. Adjust the supply and demand. Cross out the exhausted row column. 5. Recalculate penalties for the reduced table. 6. Repeat until all supply and demand are satisfied. Example. M1 M2 supply. F1 4 6 20. F2 5 3 30. Demand 25 25. Step 1. Penalties. Row F1 4 6. 6 to 4 is equal to 2. Row F2 5 3. 5 to 3 is equal to 2. Kernel M1 4 5. 5 to 4 is equal to 1. Kernel M2 6 3. 6 to 3 is equal to 3 highest penalty. Step 2. Allocate in M2. Least cost is equal to 3 at F2 M2. Supply is equal to 30. Demand is equal to 25. Allocate 25. Now F2 supply is equal to 5. M2 demand is equal to 0. Cross column M2. Step 3. New penalties. Remaining costs F1 M1 is equal to 4. F2 M1 is equal to 5. F1 penalty is equal to 0. Only one cost left. F2 penalty is equal to 0. Column M1 penalty is equal to 1. Highest penalty is equal to M1. Least cost is equal to 4. F1 M1. Allocate min 20 25 is equal to 20. Now F1 supply is equal to 0, M1 demand is equal to 5. Step 4. Allocate remaining 5 to F2, M1. Final allocations. X is equal to 20, X is equal to 5, X is equal to 25. Total cost is equal to 20 times 4 plus 5 times 5 plus 25 times 3 is equal to 80 plus 25 plus 75 is equal to 180 rupees. Easy way to remember 1. Penalty first, cheapest next, repeat till done. Next important long question is 5. Discuss the transshipment model in detail with applications. Transshipment model. The transshipment model is an extension of the transportation problem. In a normal transportation problem, goods move directly from sources, factories, to destinations, warehouse or markets. But in real life, goods may need to pass through intermediate points, like distribution centers, hubs, or transit warehouse, before reaching the final destination. This situation is called a transshipment problem. Key features. 1. Intermediate points, transshipment points, are included along with sources and destinations. 2. Supply can move via one or more stages instead of direct delivery. 3. The objective is still to minimize total transportation cost. Steps to formulate. 1. Treat transshipment points as both demand and supply nodes. 2. Define decision variables, X is equal to quantity shipped from point I to J. 3. Write supply and demand constraints. 4. Add balance constraints for transshipment points, inflow is equal to outflow. 5. Solve using linear programming or transportation methods. Example. A factory, F, supplies goods to a warehouse, W, but sometimes goods must pass through a distribution center, D. FD cost is equal to 4 rupees. DW cost is equal to 3 rupees. FW cost is equal to 9 rupees. If the factory has 30 units and warehouse demands 30 units. Direct route, FW, costs 30 times 9 is equal to 270 rupees. Indirect route, FDW, costs 30 times 4 plus 3 is equal to 210 rupees. So, using transshipment point, D, reduces the cost. Applications. 1. Logistics and supply chain, goods move through hubs, ports, or warehouse. 2. Airlines and railways, passengers or cargo move via intermediate stations, airports. 3. E-commerce, products sent via distribution centers, Amazon, Flipkart. 4. Postal services, letters and parcels go through post offices before reaching destination. Easy to remember. Think of transshipment as a via-point model. Goods don't always take a straight road, sometimes they stop at a bus stand, hub, before reaching the final station. In short, the transshipment model is like a transportation problem with extra stops, helping companies cut costs and improve efficiency.